There is nothing that causes more fascination and terror than black holes. Very strange things happen inside black holes. Time slows down so much that it ends up stopped. Any observer within the singularity would experience a different reality. We would see it frozen in time. It is as if the very fabric of space-time has been torn, and we can somehow see what lies outside this universe. Today we are going to learn about the nature of these black holes, why it affects time, and what is more, what we can find beyond. When Albert Einstein published his theory of general relativity in 1915, he unified spacetime into a single mathematical entity called spacetime. Any disturbance that affects space will affect the weather. Gravity, according to relativity, would be nothing more than the deformation of that space-time. All objects with mass deform this fabric, and the more mass, the more it is deformed, which causes the trajectory of stars and planets to be modified. That is why the moon orbits the Earth, and the Earth orbits the sun. According to John Archibald Wheeler, space-time tells matter how to move, and matter tells space-time how to curve. The deformation of space-time has been proven with the bending of light when passing near massive objects. Gravitational lenses are another example of how space-time is deformed when there are large masses such as galaxies. Einstein's field equations within relativity describe the relationship between the geometry of space-time and the distribution of matter and energy in that space-time. Initially, there was some uncertainty about how to interpret those equations in specific circumstances. But Carl Schwarzschild brilliantly solved those equations and discovered something surprising. All objects have a mass that determines their gravity. For example, to escape from the moon we need a speed of 2.3 kilometers per second. On Earth, the speed must reach 11.2 kilometers per second. This is called the escape velocity. Any spacecraft that goes at a slower speed will return to Earth, or if it is on the right trajectory, even go into orbit. But if an object became massive enough, there would come a time when nothing could escape it, not even light. Schwarzschild described in his equations that there would be a spherical event horizon in an object, where the escape velocity would be 300,000 kilometers per second. Initially it was called a spherical mass at rest in a vacuum, but later, it was thought that that region of space would be like a black hole. This is what John Wheeler first called it in 1967. Like all mathematical hypotheses and theories, at first it was thought that something similar could not exist. As we discovered that Einstein was right in his theory of relativity, we thought those black holes must exist somewhere. The solution is for an event with a large mass to occur in a small volume. This could occur in very massive stars of more than 30 solar masses. When a massive star exhausts its supply of nuclear fuel, it can no longer maintain a balance between the radiation it emits outward and the gravity that tends to collapse it, exploding in a supernova. When the collapse continues and the mass is concentrated into an extremely small volume, an object is formed with gravity so strong that it creates a significant curvature in spacetime. A black hole. Other events can give rise to black holes such as large concentrations of gas clouds or high-density areas after the Big Bang. However, they were not detected until 1964, with the Cygnus X1 black hole, and we had to wait until 2019, where a clear image of a black hole was obtained and once again confirmed Einstein's theories. Although black holes are usually invisible, and we can only detect them through gravitational waves when they form or when two black holes collide, some are revealed by the presence of large amounts of matter that revolve around them and are in most of the center of the black holes. Active galaxies. Sometimes the matter gets so hot that they cause large beams of light from which detectable X-rays emanate from the Earth, which we see as quasars. Here you can see perfectly the accretion disk and the singularity. This is the event horizon, which is the surface of no return. Any object that crosses this boundary will never return, including light. The event horizon delimits the border of no return, and once crossed it is impossible to turn back and return to the outside. In the rest of the universe, infinite futures can await matter. This area of the passage towards the singularity is the strangest, and phenomena occur at the limit of our physics. Space-time is curved so much that it causes a temporal distortion. Here we can also see how space rotates. The length of the arrows tells us how fast it rotates, while the range of colors tells us the slowdown that a remote observer would notice, until we reach the center of the singularity where time and space are compressed so much that they become infinite. Time stops making sense. The black hole singularity represents one of the greatest mysteries of our universe, but we have powerful tools that help us understand what happens if we apply relativity and quantum physics. Relativity tells us that space-time, when it becomes infinite, ceases to exist in the singularity. That means that time as we know it does not exist. In some ways it would be like being outside the universe. Relativity no longer applies. Then the laws of quantum physics come onto the scene. A possible quantum explanation for the singularity is that infinite density could be avoided by quantum effects, and some theoretical models suggest that what is at the center of a black hole could be a quantum foam or a state of high energy and density. The curious thing about all this is that there are many similarities between the singularity of the center of a black hole and the singularity associated with the Big Bang in the context of cosmology. Both points represent regions of extremely high space-time density and curvature, where the laws of classical physics, such as those described by Einstein's general relativity, reach their valid limits. Could it be that the Big Bang was the consequence of the compressed matter and energy of a previous universe that then expanded? The difference is that the Big Bang is a naked singularity and black holes are a clothed singularity, protected by an event horizon. Naked singularities could occur continuously in the quantum vacuum and give rise to infinite universes. In the case at hand, the singularity of a black hole is like an opening in our universe, and it is believed that it could connect other parts of the universe or other universes, called Einstein-Rosen bridge or wormholes not yet discovered, but predicted by relativity. The quantum vacuum, that dynamic entity from which we come, could be contained in more dimensions, but contrary to what is thought, the universe would not be a region surrounded by a larger vacuum. It would rather be a decompression of the quantum vacuum, creating a macroscopic spatio-temporal anomaly. We have always represented bubble universes floating in an ocean to understand it, but if we are more precise and realistic, the universes would be connected to the vacuum by much smaller dimensions. Representing macroscopic universes in a smaller quantum vacuum is difficult, but let's try. This is how we would see it. That void would contain more extra dimensions but subatomic size scales according to string theory. Naked singularities would emerge from the void and could be infinite. Black holes give us a clue as to what the other side of the cosmos could be like. There where relativistic laws stop working and atoms disintegrate, where time stops making sense. Imagine the time contained in a flat surface. Time always goes at a certain speed, but if that network is distorted, time takes longer to travel the same distance, although for someone who is in that curvature the same thing continues to appear. If we distort it even more, time becomes infinite from the point of view of an external observer, and it is as if it does not move forward. That's what happens in the singularity of a black hole. From our point of view, time stops for someone who enters the hole, because an infinite measure is the very absence of space-time. There is nothing that can be measured. The singularity of a black hole, therefore. It is defined as a mathematical point without spatial extension or measurement in conventional terms. This means that in order for there to be time that we can measure, we need the quantum vacuum to be decompressed from a point by means of a singularity. And here is something that will blow your mind and is paradoxical. If time stops inside a black hole, it is trapped in the same time period as its creation. According to relativity, if we saw someone enter a black hole and cross the event horizon, we would see them frozen in time, but only from the point of view of an external observer. Inside the black hole, it would have its own time and may evolve differently than the time observed from outside the black hole. However, this does not mean that time is trapped in the same time period as the creation of the black hole. Stephen Hawking proposed a mathematical solution for these cases in quantum physics. If conventional time is a horizontal line that goes from the past to the future, in the quantum world, imaginary time is another perpendicular line as if it were another spatial dimension. So that we could move backwards or forwards in that time, which means that the absence of time inside a black hole is only an illusion as external observers when we apply relativity. Imagine the quantum vacuum full of energy, chaos and infinite events where there is only uncertainty. In the absence of a conscious observer, any scenario is possible from the quantum vacuum in that imaginary time. If there are infinite alternative scenarios produced from the chaotic void. In the scenario that has decompressed the spacetime, a conscious being chooses it in quotes, collapsing the wave function and computing its time forward.